What we've done up to now is set out the sort of rules of the game. And that exam on Friday was testing you on the rules. Some of you know the rules very well. Some of you have never seen the rules before. That's the state of play in this class. It's just how it happens. We are moving now into what I consider, having struggled with some of this stuff myself at your age, some of the more difficult material. Especially chapter 5. We spent some time looking at Newman depictions. We spent some time looking at cyclohexanes from different angles, trying to work out what the relationships were between the different groups. And what we have to do now is take that a step further and start looking at three-dimensional molecules and deciding how they are related, whether they're the same thing, whether they're isomers, whether they are stereoisomers. Now, we spent some time in chapter 4 talking a little bit about stereoisomerism when we did the cis and trans and the cyclohexanes, but this is order of magnitudes more difficult. So we're going to talk about something called R&S, a nomenclature system to tell which of these isomers you have. We'll talk about the history of this subject a little bit. This is essential for anybody who's interested in passing the class, certainly anybody who's interested in medicine or pharmacy or engineering, stuff like that. This is a fundamental property of organic molecules that is confusing, and it's everywhere. So I have on the slide here 4 molecules, all of which happen to be pharmaceuticals or biologically relevant systems. And we have spoken a little bit about what the wedges and the dashes mean. The dash means going into the plane of the board, the wedge means coming out of the plane of the board, and so far that's been fairly straightforward. Well, now we have to worry about exactly what those things are relative to each other, and then how does that relate to another molecule that's very similar to it, but changes slightly. All right, so I'll point out right now something like morphine, which I consider as a professional organic chemist of 30 years, that is a complex molecule, no doubt. It has been made from scratch. It's obviously very interesting because of its pharmacological properties. It's been studied a great deal, but it is no doubt a very complicated system. But somehow, and you can learn this about somehow in biochemistry, and my class that I teach in the spring next year, 2017, the idea that each of these wedges means something, each of these dashes means something, and nature only produces one isomer, where every one of those centers, every one of those carbons, that is a wedge or a dash, could be the other. It could be a wedge or a dash. And if you start messing with that and start manipulating those directions in space, you can build an awful lot of compounds very quickly by just changing one wedge into a dash, and then doing it on another molecule and another molecule. And we'll see a formula, not today, I'm not going to rush this, it's an important subject. We'll see a formula now. If you have n of these systems which has this wedge or a dash, and they fulfill a certain type of property, you can have 2 to the n isomers. Now that becomes very big very quickly, right? So 2 to the 2, 4, and then 8, and carry on. We'll see here that this has 1, 2, 3, 4, 5 of these centers. We'll define them today as chiral centers, and if it has 5, that means there are possibly 2 to the 5 isomers of that molecule, and nature only produces 1 of them. Now this is interesting to us as chemists because what happened to the other 2 to the n minus 1? They didn't evolve, they didn't arise. Maybe we can make them in the lab, maybe they can have interesting pharmaceutical properties, and this is the idea now of chemical genetics. Where does this stuff come from? If you go to something like cholesterol, which you have seen numerous times as I've built up the context of the class, the idea of like dissolves like, and there's a polar functional group in there. For those of you who bothered to learn your pKa's, what's the pK approximately right there? 16, it always will be. Over here, very non-polar, but all of a sudden these wedges and dashes. What if I change that dash into a wedge? That's no longer cholesterol. That's a different molecule. It's related to it as a stereoisomer, but it isn't cholesterol. Maybe it will have interesting pharmacological properties. We don't know unless we make it. But if you start counting here, that's one of these centers. There's 2, there's 3, there's 4, there's 5, there's 6, there's 7. 2 to the 7 is getting to be a seriously big number. So what we'll have to do over the next few days, and I intend spending about a week on this subject because it is so fundamental, is thinking about the consequences of slight changes in these molecules and what it will do to their pharmaceutical and medicinal properties, but also how it opens up organic chemistry into this massive subject. What we have done so far, no doubt, you think about alkanes, very simple molecules, no functional groups. Once we started to get to 40 carbons in a molecule, we had a ridiculous number of isomers possible, right? Just by adding the atoms together in a different way. Now we can expand this because we're going to have molecules that are related as mirror images. And that's really the only relationship. They seem to be identical other than the fact that they are mirror images. And those mirror images will make a big difference in terms of pharmacology, but we can explode this now. We can make this a huge subject by simply changing the type of isomerism. So we'll talk about these molecules as we work our way through the chapter, and we'll think about 2 to the n. Keep an eye on that. I'm going to define it probably on Wednesday. 2 to the n possible isomers starts to get very, very big. But of course, you have to learn this stuff in such a way that you can handle it. And the textbook and what we try to do in lecture is to distill this stuff into the basic ideas and to keep it as simple as possible. It's not a difficult subject unless you don't try or you don't keep up. Then it's impossible, or you don't come to the class prepared. then it's impossible. But for the most of you who passed the first exam, this I would imagine will get more interesting, a bit more challenging, and start to become a bit more realistic. And then I'll be into 6, and 6 is where it just takes off. The chemistry takes off. So this slide is trying to define what you know so far about isomerism as it relates to organic molecules. We have dealt with early on this idea of constitutional isomers, taking the same Lego bricks and putting them together in different ways to get different shapes or different molecules. And we'll learn later on that if you look at this system down here, C2H6O, you can put it together in 2 different ways, one of which you know is an ether. We'll talk a lot about ethers later, but COC was an ether, and this guy over here was an alcohol. Those are very different chemically and very different pharmacologically. They have very, very different responses in the body. So this is a poison. This is bad news. If you drink enough of this stuff, it's a poison. Don't. But you can see now that changing the functional group and changing the structure very slightly makes a massive difference in terms of their physical properties, their chemical properties, and then later on their biological properties. So that was a type of isomerism that was fairly simple, because all you did was switch around the atoms to give you different molecules. What we did in chapter 4 was define something called stereoisomerism. Basically, direction in space. If you're pointing in the same direction in space in a system that cannot rotate, that is rigid, like on a cyclohexane ring, you with a cis isomer. If you were pointing in opposite direction, say up or down, on a rigid 6-membered ring, that was the trans isomer. And the idea of that was you did not have any interconversion between these two. So this is not allowed. You can't do that. Physically impossible. So now we have these things stuck. And the whole point of this, and be careful here, is that that cycle is key. The fact that it cannot rotate around the bonds in that cycle makes that a system that is not going to convert into the trans isomer. So most of you did okay on this. Most of you can draw cyclohexanes, which is good because you'll have to do a lot of that in the future. And we can talk now about a different type of isomerism simply by arranging the atoms or groups a different way in space. And chapter 5 now is all about an extension of that, stereoisomerism at what we call a chiral carbon. So we will see 2 types, or we will project this into 2 types of molecule. We're going to talk about the fact that maybe in a cis 1,2-dimethyl cyclohexane, there's more than one possibility. Maybe there's more than one possibility of putting these groups together to make different isomers. And not only cis and trans. We'll have to extend that into this idea of chirality. So far, cis, same side, easy enough. Trans, opposite side. Definitions that you should bring with you. We will see later on in chapter 8. And chapter 8 is huge. The chapters get bigger and more detailed from now on. That's just the way it is. And I think I'm in good shape in terms of where we are. Chapter 5 starts in the 6th week, 5th, 6th week. We're in good shape because we're going to need to spend 2 weeks on each chapter probably from now on. In this example of an alkene, we haven't seen much of these things yet, but we will spend a lot of time on them. But the whole point of putting this slide up now is to understand the basic requirements for a stereoisomer. What you need to have here is some rigidity. So what can you do around a single bond that you can't do around a pi bond? Rotate, right? Single bonds will freely rotate unless they're in a cycle, which is the case up here, and pi bonds will just not rotate. Why? Because if you do, you'll break the pi bond, and that's going to take a lot of energy. That's going to be difficult to do. So under normal conditions, that's not going to happen. So now we have a situation in which we have an alkene. The 2 R groups, in this case methyls, are on the same side of that alkene. We'll call that later on the cis alkene. And over here, they are separated and they are pointing in opposite directions. That is the trans alkene, for the same reason the isomers above were cis and trans cyclohexanes. But the whole point here is rigidity. No rotation around this bond, no rotation around these bonds. It does not happen. So these groups are stuck in space, pointing in those set directions. That's important. Feel free to ask questions, people. I can just keep going and going and going. So here we get to this chirality idea, right? It's from the Greek word for handedness, and it's a very, very important subject. If you're going to take a standardized test in the future, you will be tested on this. Beyond my class, it's really important. And we're going to say that these groups of molecules, these types of molecules exist, or they can exist as enantiomeric pairs. They exist as a pair of molecules in which one is left-handed and one is right-handed. And that's the simplest way you can think about it. So we do this every year, and it hasn't failed yet. The test for this, whether your molecules are related in this way, is to just take your hands and put them together. If you want to try and do it now. Okay? Take your hands and put them together. For the most part, they are mirror images. You know, if you've got a wedding ring or whatever, or a big scar, maybe they're not exactly the same. But they should match up, right? Pinky, what do you call it here? Pinky? Small finger over here, the rest of them go there, the thumbs go there. If you can't do this, I apologize. Okay, but you should be able to, right? Because they're mirror images. Now, the test for this, whether these are the same thing, because they look the same, this looks like it's got 4 fingers and a thumb, likewise this, is to try and put them on top of each other like that. Okay, try and put them on top of each other like that. And hopefully your thumbs don't match. Now do this, because it's something you'll spend time on. You'll go home and start scratching your heads as to what's going on here. The thumbs don't match, right? Most of us, all of us, your thumbs don't match. So they are now stereoisomers. The thumbs are pointing in different directions, the fingers are pointing in different directions. They look the same, they are mirror images, but you cannot put one on top of the other. That's the basic definition of a chiral system. Hands, left and right. So we have to extrapolate that to organic molecules, which gets to be more fun because these things usually are sp3, and we have to worry about shape. What shape is this carbon here? Tetrahedral. What are the bond angles, roughly? 109.5. Right. So now I have a blue atom or group pointing in the direction of that one. And the red atom is pointing in the same direction as that. The white is out back, the white is out back, the green is out front, the green is out front. These are your hands. These molecules are your hands. If you pick these molecules up, and we can do it in recitation with the small molecule set, you try and put one on top of the other, they are not the same. They have all the same Lego bricks. They seem to have all the same continuity and connectivity in terms of the way they are bonded, but you cannot put one on top of the other. If that's the case, and they are said to be non-superimposable, that's a word I'll put up in a second, they are going to be chiral. They are going to have this property where there could well be two of these compounds exist. So the book makes an attempt to try and persuade you that this is fairly simple to pick up. I don't think it is simple to pick up. If you get it straight away, great, be a chemist. If you don't, you do what everybody else does, including myself. You struggle with it, you ask questions, you get molecules in front of you, you get somebody like myself or Tyler trying to persuade you that this needs to be understood. It is now thinking about pieces of paper and structures on a piece of paper as if they are 3D molecules. We can do this better nowadays. You know, you've got the advantages like things like Chem 3D. You can make a 3D molecule and turn it in space that we didn't have. But we use the plastic models to be able to project a 3D molecule and decide what shape it will be and whether it's going to be chiral or not. So in the textbook, we have a picture like this, the old John Lennon glasses. At the top, you can see that both the lenses are shaded. And if you turn this around, the whole point of this is if you pick this up and you turn it around, you will be able to put that thing on top of the one on the left. They are superimposable. Both those lenses match. If you put everything on top of the pair of glasses on the left, everything will match. So how are they related? Are they the same or different? They are the same. Okay? Very simple test to be able to recognize whether you understand this stuff. Now, if we do the same thing with this, we have over here what looks like the left lens to be shaded, and over here the right lens is shaded. If I pick these things up and try and put one on top of the other, do they match? No. If you don't see that, you need to get it immediately. For those of you going to continue in the class, you need to get that immediately. If you don't see it, ask, right? So now we have a system in which they are isomers. One is left-handed, let's say, one is right-handed. We'll have a more exact definition of what that means in a minute when we do a nomenclature system, but they're certainly not the same. And you can now see why this gets to be quite complicated. So chirality, handedness, the simplest example, if anybody asks you, are your hands. But there are a vast number of organic molecules out there that exhibit this property, and we've got to be okay with this. Let's extrapolate into an organic system. You can see here two fairly simple alcohol molecules, nothing more complicated than a butanol. And we'll find out now that the projection in space, this is in the plane, this is in the plane, as is this, but this is pointing forward, this is pointing forward, this is pointing back, and this is pointing back. At first glance, they seem to be the same thing, but they're not. They are mirror images. And if you pick one of these things up, just like those pairs of glasses, and try and put one on top of the other, they won't match. Two of the atoms or groups will. If you picked up the thing on the right and turn it around, the OHs and the H will probably match, but these two won't. This will come out front, which is where the methyl is, and this will go out back, which is where the ethyl is. They will not match. So the definition now is that, in this case, the isomers are related as what are said to be non-superimposable mirror images. That has to be understood now. You cannot put one on top of the other, therefore they're not the same molecule. They are stereoisomers because they only differ by the projection of groups in space. Ashley? Yes, it will turn around, exactly. Now that's actually a very good point, because where we were last week was kind of static. We were looking at molecules from one direction. We had this little thing to try and persuade you, like physics optics. We were looking from a certain angle, and you were static. Now you're not static, maybe the molecule isn't static. You've got to practice looking at these things from different directions to be able to work these problems out, and to be able to see why this is key. We can build this up very quickly, and we can build some definitions. What are we looking for here? We are looking for something called a stereogenic or chiral center. Chiral fits everything. Stereogenic is a bit more modern because it fits all sorts of definitions, including atoms that aren't carbon. And we're looking for what's called asymmetry. So I would argue that my hand is not symmetrical. My thumb does not match my pinky, right? That is not symmetrical. That is said to be asymmetrical. So you're looking for an asymmetric system. If you have symmetry in the system, it won't exhibit this type of isomerism. If you do, it won't. It will. So what we're looking for here, as is defined at the top, are 4 different things attached to that central carbon. The middle carbon is the chiral carbon. It is the asymmetric center. It is the stereogenic center. Those are all different words you should pick up for the future. But now I have a system in which I have A, B, C, D attached to that middle carbon. That is by definition a chiral center. You need 4 different atoms or groups. And I'll say that again, atoms or groups. So at the molecule at the bottom, it's fairly easy. I've got a hydrogen, bromine, fluorine, chlorine. Those are all different. We're going to see some very complicated systems in a minute when we have all carbons attached. And then you have to go further and you have to differentiate between the different groups based on proximity and how far away things are. But right now, this is a chiral center right here. And this is a chiral center right here. So if you see this property, there is a good chance the molecule will have an isomer. Now, it doesn't have to exist in nature. Like I just said for the cholesterol and things like that, not all these isomers exist in biology. But in the lab, we often will make both of them. That's a big subject to come up in chapter 6 and 7. So very quickly, chiral center, you need 4 different atoms or groups attached to an sp3 carbon. This doesn't happen on sp2 as far as you are concerned. It does not happen on sp as far as you are concerned. It's all about sp3 carbon. We okay? All right. So what we need to do here is very quickly bring with us what we learned in the first 4 chapters and start to put in this extra idea, this extra sort of module of information. And I'm going to look at this carbon. And as you get to think about this and try to tackle it, like we did with the Newman depictions, like we did with the cyclohexanes, I think it's worthwhile putting in what's missing. We often strip out most of the information to make it quick to draw, but what's missing from this carbon that would be helpful? Hydrogen, in what direction? Back, right? It's a dash, because I've already used up my wedge, and I've already used up my 2 straight lines. As you practice, that allows you to think about 4 different things. I have hydrogen, I have chlorine, I have carbon, I have carbon. Wake up! I have carbons on both sides. We'll have to say in a minute how that is different. It's obvious that one's an ethyl and one's a CH3 group, but it's not as simple as that. I do have 4 different things attached, therefore this carbon is going to be chiral. It might have a system that is the opposite, that is the mirror image. We might be able to make it. Nature might produce it. We don't know. That's all circumstantial. But for sure, this thing has 4 different groups attached. That is a chiral center, yes. What about this thing next to it? Is this a chiral center or not? No, why not? It has 2 hydrogens attached. It does not pass your test, right? It has 2 hydrogens attached. So moving along, what about this at the end? Chiral or not? No, what's attached? 3 hydrogens, so I can't do it there. What's missing from this carbon right here? Hydrogen. So I can now think about this as 4 different atoms or groups. And you've got to be very careful here. Listening, Santigantes? Are you listening? Very good. Here I have 4 different things attached. I have an oxygen. I am carefully not saying an OH group. I am saying I have an oxygen. Because you'll have to go through this systematically and move away from that chiral carbon and define systems very, very carefully. If you said it's a hydroxyl, that's missing the point. It's an oxygen directly attached. Here I have a carbon, here I have a carbon. So far they seem to be the same thing. They are CH2 groups, but it's fairly obvious if I keep going, I do get to a point of difference, which will be the key point in our nomenclature system on Wednesday, how we tell these things apart. So this is not symmetrical. I would hope that we could see this is different to this. So there's no symmetry down the middle of that molecule. Therefore, that is not a chiral. That is a chiral system. Over on the right-hand side, I seem to have a carbon with a bromine. What's missing? Hydrogen. Where is it? Now, it does not matter if I put it to the left or the right. It really does not. You just tilted the molecule slightly. You haven't changed the nature of the molecule. So I have here bromine. I have here a carbon. I have here a carbon. I would hope it's fairly obvious that that carbon is not the same as that one. One is sp3, one is sp2. Therefore, you fill the criteria, or the criterion. You do have 4 different things attached, and therefore this carbon in the middle is going to be a chiral system. That thing will have stereoisomerism. Get this immediately because we're going to get very, very detailed on Wednesday, and this can be kind of hairy. Actually, Well, I'm going to give you a set of examples here to work through. Let's go through these things and we'll decide if we understand this very quickly. Looking at the top left, I have a carbon here which seems to be, it's suggested that thing might be chiral. It has some wedges and dashes. Be very careful. It's not always a chiral center. You have to be careful here. I have a CH3 sticking out. I have a bromine sticking back. But I have a CH2 here and a CH2 here. Before I go any further here and waste time, I'm just going to draw a line through it. That molecule has symmetry. If you were to build this as a cyclohexane system and put it end on, you could slice it in half. Because this side of the molecule is the same as this side of the molecule. So this is that they're not chiral. And we need a word for that. This is achiral. Anything that isn't chiral is achiral. It has two of the same attached, does not fit. If I move across, here I have carbon with a methyl, a bromine, an sp2 hybrid carbon, and an sp3 hybrid carbon. I cannot draw a line through any part of that molecule that shows me symmetry. This molecule is certainly asymmetric, and that is a chiral center, and that molecule could be said to be chiral. What about this over here? Be very careful. That suggests that we have some of this asymmetry. We have some of this three-dimensionality stuff happening. Is that a carbon? Is that carbon chiral or not? Who says yes? Who says no? Correct. This is where guessing and impetuousness, you're listening at the back, will ruin your organic experience. You've got to think like a scientist. I know it's difficult, but you've got to try. Those are two methyl groups. Therefore, do I have 4 different things attached? No, I do not. So that thing is not chiral. That is achiral. Down at the bottom, these are very simple systems, folks. By next week, we're into very, very big molecules. There's a carbon. I have a chlorine, a hydrogen. I have a CH3, and I have an ethyl group attached. Yes or no? Yes, that is a chiral center. That molecule is asymmetric. That thing is said to be chiral. Over here on the right-hand side, bromine forward, fluorine back, methyl down, propyl to the left. Yes or no? Yes. Now, this is the carbon that is an asymmetric center. That molecule is not symmetrical. It's overall asymmetric. It is chiral. It has this property. So it will probably exist as later on, a pair of isomers. Michaela? That's a good question. That's a very good point. Now watch this. If you put the bromine here, and you put the fluorine there, correct. That is not a chiral system because it's symmetrical. I have ethyls left and right. That's the point. Fair enough? Okay, so we're getting the basic definitions out of the way today, then we can start playing the game on Wednesday. To be able to get this is not particularly easy. It does demand some thought, and it certainly demands getting onto it as soon as you can so you don't get lost. It is very easy to get lost from now on. If we have a pair of molecules that exist like your hands, we need a definition of, they are chiral molecules, but we need something that fits a subset so that when it gets more complicated, we have something else to point at. So we're going to say now that your hands are enantiomers. This is a new word that you haven't seen before, probably, enantiomers. That is a definition of two molecules that are related as non-superimposable mirror images. Your hands are the simplest example of enantiomers. Two compounds, stereoisomers, that are related as non-superimposable mirror images. The book has some nice pictures to be able to try and persuade you how this works. You can see here this molecule amphetamine. They are not the same compound. One has a wedge, one has a dash. This carbon here is chiral, as is this one here. And what you need to do, and this is why it's tricky, is in your head, turn this around in space and try and put it on top of the other one. They won't match. If you turn this thing around in space, yes, this becomes a wedge, but your phenyl group is over here. It's like the glasses example. It just doesn't work. Practice that. Be comfortable with it, because this is the very, very, very beginning of it. When we get to Fisher depictions and all this stuff next week or later this week, wow. Okay? So these are different ways of drawing organic molecules to show the isomerism idea. You can also put these things next to each other. If this helps you better, then do it this way. Those two look like they are the same thing, but they're not. This is the mirror image of this. If I were to turn this thing in space 180 degrees to try and overlap it with that, what happens to the methyl groups? What happens to that group if I turn it 180 degrees in the plane of the slide? It becomes a dash. Everything else matches, but that doesn't. So two groups will match and two groups won't. That's the whole point of that simple asymmetric center. Ashley? In that example, yes, because then it would be symmetrical because you'd... No, my bad, sorry. Even getting rid of the phenyl group, because you have that NH2 out there, it still has 4 different things attached. It is still a chiral system. Okay? As long as you've got 4 different things on that one carbon, that thing looks like it's chiral. And it has this property. Now, quick story to finish up, and then we'll give the exam back, and then you'll go think about your lives, and then we'll come back to this on Wednesday. Jordan. Yes, it very much does. I'm looking at this carbon because that's the one with the wedges and dashes. That's the one that is potentially chiral. The other ones, no. sp2 can't be chiral here. This has got 2 of the same things attached. That isn't a chiral center. Now, why is this important? Anybody who's interested in pharmacy or medicine or clinical laboratory science, anything on the biological end of things, needs to understand this story because it's really important, and actually it's a topical from this year. Molecules that exist as enantiomers, your left hand and your right hand, can be dramatically different, right? I am so right-handed that my left hand is just for symmetry. I mean, that's as bad as it is. I'm the most right-handed person you'll ever come across. This is useless, right? But that's typical of sort of organic compounds when it comes to medicine. You think about systems that look similar, but they have this property. On the left, we have something called carbone, which is the R+, R-. We'll define what that means on Wednesday. And on the right, we have the other hand, S+ carbone. Those little definitions will be done on Wednesday. All they differ by is the stereochemistry at one center. Well, your nose can tell the difference. Your nose is an incredibly complex organic receptor, organic recognition unit. Are we awake at the back, or are we bored? These molecules smell differently, okay? I'll tell you for Wednesday, they have the same melting point, the same boiling point, right? They pretty much are the same thing until you start doing things like pharmacology on them. You can smell that they're different. One of these things smells like spearmint, and the other one smells like caraway seeds. I'm not sure what caraway seeds are, but apparently it smells like that. They smell dramatically different. And why is that? It's because your nose is a chiral receptor, or it has thousands of chiral receptors, which will recognize the difference between the two, which will trigger off some different mechanism in your brain to say, that smells like spearmint, or that smells like caraway seeds. That's pharmacology. That's all you need to know about pharmacology, right? At the bottom is the more dramatic example. Now, this is something that's very topical because this is now used as a anti-leukemic drug. It was brought about in the late 50s in Europe and in Britain. This is thalidomide. Anybody heard this story? You should have heard that. You should hear this story, and you will know it in the future. This mixture was produced and sold as a mixture of the 2 compounds. One of which is, let's say for now, left-handed, and one of which is, let's say for now, right-handed. The problem is, and this was actually given to pregnant women to alleviate the symptoms of morning sickness. So one of these enantiomers does a really nice job of alleviating the symptoms of morning sickness. But the other enantiomer, I think it was this one, is a teratogen, right? What it does is it cuts off the blood supply to things that are starting to grow, such as a fetus. Right? So there are a generation of kids, there are thousands of kids across Europe, who were born without arms or born without legs. Their hands were joined at the shoulders, or their feet were joined at their hips. And a lot of them survived, some of them are still going. But it was really sad, because the regulatory agencies in Europe had not done a good enough job of working out what this compound did. Right? The mixture was sold, it did what it's supposed to do, but it also did other things that came out later that weren't in the clinical trials. So this was a disaster. Right? This is a real disaster in Britain and Europe. And it sort of set up the modern regulatory ideas that you must test a drug as thoroughly as you possibly can so it does what you want it to do and doesn't do anything else. Right? That's a really important thing. And the reason I bring this up now is this past August, the woman who was responsible for this not coming to the United States, because the company wanted to sell it here, and the Canadian physician, Francis Oldham-Kelsey, who was working for the FDA in Washington, D.C., said no. We don't know enough about this drug yet. This was before all these deformities, right? We don't know enough about what this drug does. And she put her foot down and said no. She passed away 101 years old in August. And if it hadn't been for her saying no and putting her foot down, you'd have had the same problem in the US, right? Absolute disaster. So when people complain about regulations, here's a good reason not to. Here's a good reason why we need some of them. So what I'm going to do now is talk about this last word for today, to set you up for Wednesday, and then come back and talk about this in more detail. We now have a pair of enantiomers. We can have 2 compounds that are related simply by being mirror images. one of which can be good and one of which can be bad. Ironically, the bad thalidomide is now sold as an anti-leukemia drug. Because guess what you want to try to stop growing in a person with leukemia? Tumors. You want to cut off the blood supply. You want to do exactly the same thing. So now it's used for that. These enantiomers now can have dramatically different properties simply by switching the direction in space of one of those pieces. So we have a pair of enantiomers. On Wednesday, we'll define what they are. We'll come up with a set of rules called the Cahn-Ingold-Prelog rules, which you will learn and never forget, ever. That will allow you to define one versus the other. Instead of us using left-handed and right-handed, which is just silly, we'll be able to use R and S. We'll have a definite definition for what these things look like and be able to use it. So by Wednesday, you need to have read this so that it isn't just a bunch of nonsense.